welcome to the Go Meetup at Schuberg Philis. Glad to see so many of you here. Yeah, it doesn't seem to want to work. Yeah, who are we? We're just people from the community. And the reason why we started this one is to give back to the community and also share our experiences, help further build the community, foster professional development, and also connect people that are interested in Go to experts. And I want to say thank you first to Schuberg Philis for hosting this event and for the amazing food and venue they provided. That actually happened. They burned the ship. I don't know when or where it was, but it was before my time. Yeah, also, it was 2 years ago. As to why? Do you know why? Oh, Family Day. Yeah, the logo. Yeah, there's a logo with the logo, as you can see on the bottom, is a sheep. So, to be honest, it looks kind of like a Trojan horse. Oh, it was, huh? Yeah. Tommy, catch.
Picture of a sheep and then you're sheeped. It's a running gag within the entire company to remind you to lock your laptop when you walk away. And so for this event, we burned a sheep. That was it.
Yeah. Okay. So here are the talks that we are going to be having. First by Koray about OpenTracing, then by Jacob about middleware. Then we're going to have a small break, and then we're going to be hearing about unikernels by Michiel. So I would like to ask Koray to come here while he sets up. I would like to ask anyone that takes pictures, if you can, please upload them to the Meetup page.
Okay, thank you. Hello, everyone. Today, my topic is about OpenTracing, and I'm from I would work in text kernel. I'm just a software developer at text kernel. And let's start. So, has anybody heard about distributed tracing, OpenTracing? Yeah, pretty much. And what's distributed tracing? So before I enter that, just the graphic at the left side, new concurrent models. So when we look to the left part, it is the one that we are mostly accustomed. So in a one monolithic application, we have different concurrent models. But because of some reasons, like just the performance or memory or for scalability, we already shift to microservices, or we started to use external services. So it already introduced, as like in the right side, different services already consume and respond back to our services. So that really makes tracing the request through the whole microservices difficult. So what distributed tracing already help us for is already good for us for profiling and monitoring the applications. We already heard about APM, so Relix and other kind of solutions. And other really useful part of it, so whenever just a failures already occurred in some place in our application, it helps us to identify where the problem is. So, by the way, I already referenced those pictures at the end of the slide. They are not just a mine, to be honest. And so nowadays, new popular trends, and there are lots of reasons, I will not enter those. We have monolithic applications, we split them microservices. But that doesn't mean that we already just destroyed the monster. It already creates lots of monsters, lots of problems for us. So under those circumstances, what is OpenTracing? Where does it sit under distributed tracing? Actually, OpenTracing is an API specifications. So it helps us how the distributed tracing goes across microservices and how the developer should instrument with the code. But there is one point that we have to clarify. It is not a standard. It's not a standard API or standard protocol like just HTTP or MQTT. But anyway, just under CNCF, it started to be an official way to handle those distributed tracing. But already there are just some couple of things that already goes on to make it not again standard, but just a certain API that we can use under CNCF umbrella. And good news, that is OpenTelemetry. I'm not just including other distributed tracing model, it's OpenCensus. So when you already search in the internet, already people are in the middle of comparison with the OpenTracing and OpenCensus. And OpenCensus from Google world, OpenTracing from Uber world. So they were already beating each other. But just the good news, instead of just beating each other, they already negotiate and they already just created a new API standards, like his name is OpenTelemetry under CNCF. So for today's talk, I will explain OpenTracing, and also there's a OpenCensus, but to be honest, they're gonna deprecate it after 2 or a couple of years. So, but also OpenTelemetry is under the same way, in the same resolution. Also, it's backward compatible. For if anyone wants to just understand about what is OpenTelemetry, you can follow the links. Actually, there's also a good sentence that I like. So the greatest promise of OpenTelemetry is a standard for observability instead of 2 competitive standards. So under OpenTracing or distributed tracing, so what are the elements that we have? The main focus area in OpenTracing is unique ID that already distributed across all your application. So that unique ID already specified the relation is the first important point. Other important point, when we already have a span, just a knowledge, span item in the distributed tracing. Span means like just your isolated unit of work. And also those spans can be dependent on each other, like parent-child in here. For instance, B depends on A, C depends on B, or they can follow each other. First, you do some, for instance, DBA actions, then you log some things, then you do some another request to some endpoints. So, so OpenTracing is just a tracing, but we have to store those things in somewhere. There's so multiple applications that allow us to store those traces. One of them is Jaeger, already developed by Uber. And also there's Zipkin, and there are multiple choices also as well. In there for the demo, I'm gonna use Jaeger UI to show how the tracing already looks like when it's stored in a UI-based application to show us the relations across the request. So how we extract a span? I would get a sample from Go application. What I said in the beginning, the important point in here is the unique ID, the request ID. So in HTTP request that we're gonna handle in there, also you can have, if you already applied with just a, it can be a gRPC call or any TCP call across your application. We already extract that unique ID from the headers. Then, from our unit of work in here, we start a span. So, also, in our multiple microservices, we can get a request that already includes request ID. And what we say at the beginning, we will have multiple microservices, or in our multi-application, there will be multiple layers. So while passing through our request and context ID through the downstream or other microservices, we have to inject that unique ID to let the tracer UI to create us relation across one perspective. So in tracing, distributing tracing, there are two notions like child of. I mean, one span might be child of another span, or there would be follow-up actions. So in child of span, we already specify, in here, while creating span, is a child of my previous unit of work. If we wanted to follow up, if it's a totally different process, we just mention in here as that my span is the follow-up the previous span. And tag. Just mostly if you are accustomed in CNCF or Kubernetes, there are just label selectors. So that tags are already used like selectors. It already helps us to search across our traces, depending just the key values. Like you can search something which my services already get HTTP method as a HTTP status code as a 500, 5K, or 2K, or you can specify more specific tags there, or you can search. I would like to retrieve all my GET requests in my system, and I would like to observe the time roundabout about how many times those services already got to run. Okay, so we already have a demo. I already pushed the sample in my GitHub repo. You can reach and play with it whenever you want. Okay. So in our sample application, I already introduced two services, dump services, front end and back end. And front end already just we have like API gateway, and it requests through the back end, and back end already stores the information somewhere. So can everybody see it, or do you want me to make it a little bigger? Bigger, so good. Okay. So I'm just running my front end, back end, okay, and diagram. First of all, let's see how Vmgo looks like. Now I haven't sent any requests, so I don't have anything there that shows me about my problems. I will specify also in README like just how you can run it. I will just send just a HTTP request. And we already have errors. So what we say in the beginning, so if you already have multiple microservices, it's sometimes really hard to deal with where the problem is to point out. So let's go one by one. What the problem is there. So to a little bit just say about the UI. In here, we can specify what kind of services we want to just fetch the traces for. And in here, we can specify what with tags like I want to sort out, list those tags which I get that values. But for now, just I will just select all. And in here, it already says like just it is how the display of tracing. It is the way of DAG way of showing the trace. So this is my main request, all just the request that from my client, from terminal. It all has through the front-end part. And in here, just with the red ones, we can see like there's some errors. So it already shows us where just already error happened. It's already just, I know the code from there. So absurd already takes place, just a problem when the Redis is not there. So also from the here, we can see, let's open this one, Redis absurd. Okay, so let's start the Redis then. Okay. Find traces. Now we have a HEP scenario. So let's talk about a little bit how we can read that actually UI. So I would like to go to my console first. Let's do one more call. Okay, so when already my request comes in, and this is because of already developed by Uber, we already have a trace ID. In OpenTelemetry, we have more standards, right? We don't have OpenSensor or Uber kind of things. So that unique ID already tells us lots of things. It says in here, with that ID to end that ID, it doesn't have any child or follow-up. This is my root request. So if we just have a look to that ID, 56, and if we go, let's open this. If you already notch down, there's a little ID, 56. This is my root span, my whole request. So from there also, when we go a little bit down, from there we already see like this reported things. At the beginning, I already say we already have in span child or followers. So this one, if you look through the ID, 7D, and if you look there, 7D. That my 7D in here is already full of 55. So when we go to UI, 55 there. So in here, those are all child of relations. And if you go, for instance, there, 65 already child of that root context. And also 17 is child of 65. Another just a way that to see the relations from UI, you can say trace JSON, and from there you can already follow up who is relating to with whom. Is a child of, follow of, under the same span. Yes, that's it. Those are the references. Also, I really suggest to read that book. I'm not just making an advertisement. I'm not just taking a money from that guy, but just is a good book. Yeah. Any questions?
So in your code you show like wrapping the parent context. The context itself, is it like a Go context? Or
Yes.
is it like
Exactly.
it's a normal Go context?
Yeah.
Ralph, can you throw the catch me box? Yeah. So whoever has questions, please speak into that. Otherwise, we can't really hear you.
Yes, so I'll repeat the questions. The context that you generate on the library, is that a normal Go context, or is it like package specific, the tracing context?
Actually, it's supposed to be. I have to double check. So, yeah, I'm not that sure for that one, but it's supposed to be just a normal context.
Can I ask the second question? Yes. Like, how do you control how many span there is? So, like, if it's really heavy traffic, is it like sampling, or can you control it? So, like, for this request, I pass something, and it's actually create a context. Or how does it work?
It's actually depend on how you code it. So, for instance, in here, I already make a lot of noise in the code, like this. I already start spans whenever just I can. So there's another option like after those number of traffics, close the spans. Don't create spans, or create the spans just randomly. Just if you already coded there, if it already hits there, it creates spans. So you actually programmatically code the spans and child of follow of relations.
Cool, thank you.
Anyone else? Yep, pass the box.
I think this is a follow-up question. So you put the spans in the code, your app starts making spans. Do all of those get sent to Jaeger? Does it
Yes.
push them to Jaeger, or does Jaeger pull them?
It pushed the Jaeger.
So your app will push everything?
Yes, from the UDP socket. Is that a TCP UDP?
Mm-hmm.
And it sends all of
Yeah,
the things.
so you have the potential of overloading that. Like,
Yeah, just a,
I've seen things like that go wrong.
for instance, you already have a high frequency trading, for instance. I would not suggest this.
I think it can go wrong with even something less intense than high frequency trading, but okay. And then I suppose, so everything goes down the Firehose to Jaeger, and then Jaeger does sampling, or it throws away things? Or
Jaeger already is the storage of those traces. Behind Jaeger, you're supposed to store in Elasticsearch or Cassandra. It depends on you, your configuration. And also while just creating those relations, another things, a Spark kind of things supposed to work. There needs to be installation for handling those traces.
yeah, but normally you keep all of them in the back behind Jaeger?
Yes.
But you have some expiry window, and then you toss
Yes,
out the old
exactly.
ones.
You also set some expiry, like the windows. But behind that windows, it always stores all of it.
Any further questions? And I would like to say thank you. And now, Jacob, can I call you to the stand?
Okay, hi. So I'm going to talk about middleware for gRPC servers. My name is Jacob Vosmaer. I'm a staff backend engineer at GitLab. I'm a bit of a GitLab dinosaur because I've been there since 2013. And my daily work is now on Gitly, which is the RPC backend for storing Git repositories hosted by GitLab. So GitLab is this software development, do everything monster application, but It started out as code hosting, so that's what you probably know it for. So code's Git repo, and then in the back that goes into this RPC service. I'm not going to talk about that RPC service today. I'm going to talk about gRPC, because that's what we used to build that thing. And first I'm going to briefly remind you, or tell you, in case you don't know, what gRPC Go server looks like. And then I'm going to look at some nice things you can do with middleware, or that maybe I should say you have to do with middleware. The first example is panic recovery. The second example is logging. And the third example is authentication, which is a bit more complex. So there I'm going to share some opinions, time permitting. But I'm going to start with less opinion and more just, I think, facts. We'll see. So what is gRPC? It is a remote procedure call framework. It's a clean room re-implementation of something Google built internally, I guess. You can use it in multiple languages, including Go, of course. And it's really built on HTTP2 and protobuf. You don't have to use protobuf, but it's the recommended thing. My experience is based on this one thing we built in gRPC. And we started building that over 2 years ago. And some of these things we just put in the beginning and it worked and we never touched them again. So maybe some of my knowledge is outdated. So if I say something that sounds outdated, please let me know during question time. But I did check. I think it's up to date, but I think it's also possible that I'm behind on some things. Because if it works, why change it? So gRPC Go server starts with a protocol definition, and this is written in the protobuf interface definition language. This is from the standard example in the gRPC Go repo. So this is a server where you can call an RPC called say hello, and it takes a hello request and it returns a hello reply. And those things have this schema, so the request is a string field called name, and the reply is a string field called message. So it's fairly self-explanatory. So after you write this, you need to run a special code generator on that, and that will create a .go file for you. And then that .go file is like it's a package you will include into your Go application, so you use it like library code. And the important things in there, in this example, is that your requests become structs. So we had a hello request with a lowercase name, but in Go, a struct should have a capital letter on exported fields, so it becomes capital N name. And every RPC method in your RPC service becomes part of an interface. And that's a simple signature. It takes a context and a request, and it has to return a reply and an error. Then you have to write some code. Well, I didn't. I copy-pasted this from the example in the repo. But this is what a server would look like. And I'm going to just walk you through what's happening here. The RPC was an interface. So we need to create a Go object that satisfies the interface. So that is going to be that server struct. Now, that struct won't have any methods. And as a convenience, you can put that unimplemented greeter server in there. That is a piece of code that's created by the code generator, by the gRPC code generator, and it has dummy implementations of all the methods. That's really nice because now, even if you leave this out, it will compile. Because if you have an interface, or you try to do something with an interface and Go and you don't define all the methods, you get a compiler error. And by putting that thing in there, by embedding that type, you at least get everything to compile. So that's a good thing to do. And then to satisfy but to have a non-trivial implementation, you just create a method on the type this is a very simple thing. It just sends a string back. And then in your main function, you need to do some more work. You need to create a listener, just a standard library listener. That's one of the nice things with gRPC Go is that it uses a lot of the Go standard library. So it uses standard Go listeners. If you want to listen on the Unix socket, that will work as well. It doesn't care. It just uses a Go net listener. You create a server object from the gRPC library. You register an instance of that special implementation class we made. And then you go into a serve function, and that will run until the end. That will keep answering requests until the end of time or until your program gets terminated, and then you hit that line. So that's what's happening here, and this is a pretty much complete example of a gRPC Go server. So what if there's a panic in that handler function? Now, the pattern you just saw looks familiar to how you write an HTTP server in Go. And you may know that if you happen to make a mistake somewhere in your HTTP handler and you panic, then that gets handled gracefully by the GoNet HTTP server. gRPC Go does not do that. So you make a mistake with a nil dereference or an index, like you index into a slice without knowing how big it is, you get a panic, boom, your server crashes. I was not so happy when I found out about that. And I think this is for me, this was the most natural example of why you want middleware. Because gRPC Go doesn't solve this problem, but you can solve it by adding middleware. And there is this project or this group on GitHub called gRPC Ecosystem. So that's not from the official gRPC project, but it contains a lot of cool middleware. So I think the main summary of my talk is if you want to build a gRPC Go server, not all the batteries are included, go there. But yeah, I'm going to expand on that. So there you can get, they have a package called gRPC Recovery, and you can get these interceptors. You install them into your server as options. Remember that we created this gRPC NER server in the implementation before. So you put this in as options, and now if there is a panic, it gets caught, and your server doesn't crash. Woohoo! Something funny is going on here. Why is there a stream interceptor and a unary interceptor? I don't know. There's not a good reason for this, as far as I know. I do know that in gRPC you have streams, which is really nice. So in a normal HTTP API, you do a request, you get a response. That was it. Thank you. Bye-bye. And in gRPC, you can say my service takes one request, but then it returns one message or two messages or three messages, an arbitrarily long stream of messages. So all of a sudden, you can implement more complex things. You can also do it the other way around, where you say my RPC will take some stream of incoming messages and then answer back with one message. You can even do it both ways, where your client sends some messages and you send some messages back, and then you have some more messages going back and forth. So you can have really complex interactions between your client and servers because of these streams. So that's why streams are cool in gRPC. I don't understand why you need two functions for this, but that's just how the library is designed. So that was panics, the problem we didn't know we had, but the problem we have. What about logging? Because that server I showed you earlier, if you run it, you can make requests, but you see nothing. And I think it's nice to have an access log. You don't always want to see that, but often you want to have a log somewhere where you can just see every request. So you can solve that by throwing more middleware at the problem. And again, in the gRPC ecosystem repo, there is a nice middleware that integrates with Logrus, which is a popular logging library for Go. So you create a Logrus entry, you inject that into this constructor class from this gRPC Logrus package, and you plug it into your server, and now you have logging. Except you can only put one middleware in your gRPC Go server. What were they thinking? So again, the nice people of the gRPC ecosystem repo made a middleware that lets you chain multiple middlewares and calls them one after another. That's another battery that's not included, but it's in there. So what's happening here is that I say to gRPC, the one stream interceptor you have is actually a chain thing, a chain interceptor, and that chain consists of these two things. And because you have to define stream and unary interceptors separately, I have to repeat the whole thing here. That's how it works. But the good thing is, it works. So you do that, and I ran this still with that panic in there. So you get a nice error where you see the message from the panic, and it's also structured, so the gRPC code is separated out for structured logging. It records your deadline, the time it took to take the request. Also very nice, your service and methods. And this logging is very useful, and it's very cheap. Like, you need to know it's there, you need to get some extra packages, but then, hey, you have a nice access log. So that was logging, and you can do a whole bunch of extra fun stuff with this. Again, I'm basically advertising that repo. If you want to have custom fields in your logs, you need to use something called tags. I'm not going to show you that now, but it works, and you can have custom fields in your logs. Like if you, because that log message I showed you is very generic. It only knows about your gRPC call has a service and a method, and it takes some time, but maybe you can say something more interesting about like who is making the call or what object is it calling on. You need to write some code to get that into your logs. Also very nice is they have a Prometheus library, so you can make dashboards with your request rates and your error rates. And one of the nice things about that is that it uses a kind of introspection. So you put that into your server once, and if you define new methods in your gRPC interface, you don't have to update your Prometheus counters. They just get added automatically at runtime. Okay, now the topic where I have opinions, authentication. So it's, yeah, if you go to the homepage, it says gRPC, it has all the things, it has authentication. I think, great. So what does that mean? And then you start looking, and you don't find a lot. And maybe I don't look right, but the only thing I find is you can use TLS client certificates, or you can use Google OAuth tokens. And then if I read very carefully, and again, maybe I'm reading wrong, the second option only makes sense if you make gRPC calls to a Google service. That's really cool, but if you're writing the service and you're not Google, then that doesn't do anything for you. So, TLS client certificates. Who knows what TLS client certificates are? Who has ever deployed them? Yeah, so what TLS or SSL is the thing that's encrypting your HTTPS connections, right? And usually it's only used in one way, where a client can check if the server is who they are. And then you do some crypto magic to establish an encryption key for your connection. But during that handshake, you can also do an optional extra step where the server checks if the client is who they say they are. And for that, you need another certificate on the client side. And that is what client certificates are about. So if you want to do that, which seems to be the only real option for authentication that is built into the gRPC Go library, you need certificate authorities. You maybe one, but maybe you want two, like one that creates the client certificates and one that creates the server certificates. I don't know, you can get really crazy with this really easily. And you need to store those securely. Then you have certificates for your certificate authority, and you need to deploy those onto all your machines. Then you need to create key pairs for the client and servers. So then you need to securely deploy private keys to the servers and to the clients, and the certificates on both sides. And I guess that's enough, because then the CA says the certificates are okay. But you need to do all that securely. And in the certificates, at least in the server certificates, you need to write the host name of the server you're talking to, because that's one of the it's this famous thing you can turn off with SSL. Like, if you don't want to verify, that means like, hey, there's a certificate. I don't know who it was for, but it's a certificate, so let's go on. And that's considered bad. So in the certificate, it says, I am this server, like I'm google.com. And so if a client wants to connect to google.com, they're supposed to check that certificate actually says google.com and not something else. That is a real pain in practice, because it means you can only create a certificate if you know what the name is going to be that the client uses to connect to your server. And because it's a pain, lots of people, when deploying TLS, just disable that part of TLS, but the gRPC library is quite pedantic and doesn't want you to do that. It depends on the client, but some of the gRPC clients just refuse to disable that. So you have to do TLS properly. And you have to deal with client certificates. So for us, this was not realistic because GitLab is, I forgot to say this, but there's an online version called gitlab.com, but it's also an application, it's an open source application you can just download and install on your own server. And I don't know the exact number, but it has over 100,000 of such installations. And we want anybody who's running that to be able to use this authentication, that whatever we're building into our service. So if it is some awful pain of dealing with certificates, and 100,000 people, well, not every one of them is going to do that, but even if 1,000 people have to do that, that is not nice of us. So we have to be more considerate than most people of how much pain we inflict on whoever has to deploy our stuff. It has to be easy. So this was not an option. So some more considerations about this. We have some automation to make it easier to configure and deploy GitLab, but that is designed around single servers. So it's very easy to deploy GitLab on a single server. If you want to split things out into multiple servers, you have to do more work, and you have to do more work manually. So this whole TLS problem then becomes the manual problem of whoever is setting that up. We considered some creative solutions where we do something with the host name where it always works, but it was getting very creative, and I didn't like it because I think it would be literally hard to sell. Because what happens with this sort of thing is one of the ways GitLab makes its money is that it sells support contracts to large organizations. And these people are careful about buying software that looks like it's built properly. So they'll have checklists. It has to be able to do X, Y, and Z. And it will have a security checklist. And that will say it has encryption. And if somebody who is doing that checklist then comes upon this creative solution and is thinking, so they're using TLS, but they sort of disabled one thing and it still works and it's kind of encrypted or it's kind of authenticated, they're not going to tick that box. And then they don't buy a contract and we don't get money. So no, we're not doing that. When we were working on this, I don't know how good Kubernetes adoption is now, but it was nowhere near as big. And we don't want Kubernetes to be a requirement for doing this. Also, service meshes sort of solve this problem, but it's not clear to me exactly how mature that is. And we're talking maybe 2 years ago. How mature was it then? So we couldn't go there. Now, if you're developing a gRPC Go server, you may have none of these problems, right? Maybe you work in a big organization where everything is figured out about certificates and just say, to your administrators, put some certificates on it and they say, sure, and you deploy and you're done. So think for yourself if this is hard for you, but for us, this was hard. Okay, a bit more ranting. Oh no, not the ranting. So what did we do? We just put a static secret in there in the header, and we check that on every call, hey, is the right static secret in this call? And then if so, then it's authenticated. It goes through. And then we got a security review, and somebody said, yeah, it's nicer if you don't send the static secret down the wire every time, so how about you use an HMAC timestamp scheme? That basically means that the client says, the client can prove it has a secret, and it signs a message that is then valid for a certain amount of time, and the server can verify that it was signed by the client, but you never send the actual secret across the line, so that's nice, but it's more complicated. We had to write it ourselves. And it wasn't actually the best fit for our architecture. But I did learn one very important thing. If you have to go and invent your own authentication scheme, put a version in there. Because we had a base 64 string as the bearer token. And we figured that it was very unlikely, or maybe even impossible, that it started with v2 dot. So that's how we could distinguish the two tokens. But that is no fun. So just put a v1 dot on there, and then whenever you get to v2, then you can do a smooth transition. Version numbers, who would have thought? Okay, the good thing is that the gRPC ecosystem has a middleware for that. So all we had to do is write a function that gets a context, and the context has the headers in there from gRPC, And then it can return an error with the gRPC code saying permission denied, or okay, and then it goes through. So it's a really nice little interface, and we plug that into that middleware, and then we have authentication. So that was good, and it's easier to deploy for everybody. But what is not nice is that we have to write authentication logic and be super careful because security and yeah. So now nearing the end of my talk. Conclusion, nice middleware from these people. Authentication batteries are not included with gRPC Go unless TLS certificates are your thing. Thanks.
So you mentioned it's difficult to deploy the PKI on both sides.
Yeah.
So what about deploying, providing username and password for the clients, but use PKI on your side and use PEEP for that?
So actually, that's what we're doing. We did this orthogonally. So we said the clients must put a static secret in there, and some people say, okay, this is okay. We're just sending this static secret unencrypted over the network because there's a firewall and it's an internal network, and Postgres also doesn't encrypt it and whatever. And some people say that is not cool. We want encryption. So then the server uses TLS certificates and just normal, like regular certificates. And the client instead just uses the password token to identify. But we leave it up to whoever's deploying how far they want to go with this, because automating the server certificates are actually harder because they have, I don't think their client has a name that gets checked. So as long as you prevent a valid certificate, then as a client you look okay. But with the server, then it also has the name that matches the host name that the client is connecting to. So that makes it harder, because if you want to automatically generate that, then somebody needs to somewhere write down their network topology and what things are called before you can generate the certificates, and then you need to move them to the right server. And it's not rocket science, but it's surprisingly hard to make this nice, easy and foolproof and automate this well. And if you do it wrong, then you have an outage. So because wrong certificate, go away, outage.
Any more questions?
Hi. You mentioned the OAuth is supported by gRPC, but you didn't use it because you said it was a Google closed thing.
Yeah.
However, later on you use a bearer token, which is exactly an OAuth principle. So,
well,
how does that add up?
The way I understand it, and the documentation is, I think, not very clear, is that they say that if you have a client, a gRPC client, if you're coding that, then you can use some code in the gRPC library to connect to a Google service. But we are building a server. So they don't give code where you can say, I'm a server and I pretend I'm Google. And yeah, so underneath it uses a bearer token, but we had to come up with our own bearer token. And it was simpler to have a static secret and say in the config file, this is the secret. It's nice if you have OAuth and you can say, I trust that thing, so I go and you say I'm okay, and then I pass in the token. But that would have been more complex than we were happy with.
Yeah, because you didn't have an OAuth in the first place.
No, also, it's that, but it's also not clear to me that even if you would bring your own OAuth provider, that it would work. Okay. I have to say, I didn't look too closely at so the documentation says just only use it for talking to Google. I didn't read the library API very carefully to see if that's the only way you can use it. But my gut feeling was that we're not using OAuth to connect to Postgres. We're not using OAuth to connect to Redis. And within our architecture, this service is comparable to those. So if we say you want to deploy this thing, and now you need to set up an OAuth provider so that a front-end component can connect to your back-end component via OAuth, it didn't seem like a good fit.
Yeah. Okay. Thank you.
Try. Come on. You can do it. Almost.
Because you said about the checkboxes.
Yeah.
So in the end, you don't use TLS certificates.
Well,
Still.
no, we have support for putting TLS certificates on the servers, but we don't make it the only way to have authentication. So I think this is, so if you're an organization that cares about this, then you have your TLS stuff in order. So then you can, it can do the work of putting TLS on there. So it's two separate layers, encryption and authentication on separate layers. The nice thing of client certificates is that encryption and authentication are on the same layer, which is kind of cool, and then everything is encrypted. But if you make that the only option, then only the people who have the operational maturity to do that can use it. And by using tokens, people who do not have that operational maturity, which frankly includes us, can use the tokens and at least get started and have something.
Okay, cool. So you're using two, or you're giving them, you're leaving the option open for them to
yeah,
send
it is. It's yeah. Well, the default installation is on one machine, and there we use a Unix socket in a directory with restricted permissions, so that only the application user can get in there. So then there is no token, because if you can open that Unix socket, then you can open all the Git repositories on the server, and it makes no difference. So yeah, we have different levels and different options.
No more questions? Great. Looks like that's it. Thank you, Jacob.
Hello everyone, my name is Mechiel Lukkien. I'm going to talk about my new research project called Vmgo. I really like this project because it allows me to combine lots of things I find interesting. Of course, Go is one of them, but also security and more of a systems architecture. So I'll be explaining today what this project is all about. It is work in progress, it's not yet finished. It's probably broken in many ways. I'm sure it's broken in many ways. So, disclaimer. There is code already online on this GitHub repository, so you can see what I've been doing and what I'm talking about. So for today, I've got this table of contents. First, I will explain the goals of the project, why am I doing this, and also a bit of background, so to help you understand what this is all about. Second, I'll be explaining a little bit the work that needs to be done then to attain these goals. Third is the approach I've taken in doing that work. And fourth, I'll be explaining the current state of affairs, how far I got so far, and then I'll have explain some ideas for the future. So first, some of the goals. I want to be able to run my Go programs, compile them, but then run them in a secure way, in an isolated way, with a minimal software stack. So that's sort of the challenge that I've set for myself, that I find interesting to research. Because if you look at modern software stacks, there's a lot of software involved, from the hardware to the operating systems running and the application finally, and all the stuff that's surrounding there. So the idea is a bit to see how far we can trim that, how much of the fat I can remove. So the approach I'm taking is twofold. One, I'm trying to apply unikernels. So I'll explain in a bit what unikernels are. Who has heard of unikernels or know what they are? Okay, it's a few hands, but I guess it's good. I'll explain it a little bit, and I will use a small hypervisor. So who knows what a hypervisor is? Okay, a little more people at least. So that's how you do virtualization. So first, a little bit of background. This image, hand drawn, is a sort of simplified depiction of a machine running some applications. So at the bottom we have the hardware, that may be a laptop or a server. Then you've got a operating system kernel I'm just writing here Linux kernel, but I know there are many more different kinds of kernels, but essentially they pretty much do the same thing. And on top of that, we have several applications running at the same time, or at least seemingly at the same time. Now, the job of the Linux kernel, the kernel, is to drive the hardware, so the network controller, the disk controller, display controller, keyboard, mouse, etc., and also to provide an interface, sort of a abstracted execution environment for applications, and also to isolate these applications from each other. They should not be able to influence each other. So you may know the term user space. That's where the applications are running, and you have the term kernel space, and there is a security boundary between those two spaces. And in the Intel architecture, you've got the privilege level 3, which is called ring 3, and ring 0 for the kernel. Now, the application is isolated. It can just run instructions, but for some special things, it needs to ask the kernel to do some work. And it will do that by executing a syscall instruction, for example, to open a file or to create a network socket. So then the kernel handles that call and later continues execution of that application. Now, if the Linux kernel wants to do something special to the hardware, it executes an I/O instruction. That's how it talks to the hardware. If the application would try to execute an I/O instruction, this would get detected, reported to the operating system kills the application. So this is sort of the simplest way we currently run our operating systems and our software on our laptops. Now, unikernels is simpler. We've got the hardware, that's still the same, but then with unikernels we have one application running, not multiple, just one, and we've basically removed most of the kernel and moved a little bit into that application. So really just have a sort of a little bit bigger application, but not any kernel anymore. Of course, then you would have, the unikernel would have to drive that hardware, so that's a sort of a new task that it would have to do. So that's one of the things I'm interested in. Then the first picture is not how we actually run our software in the cloud. If you run software in the cloud, it looks a bit more like this picture. We still have the hardware on the bottom. Oh, I meant to say we're using virtualization in the cloud. So we have the hardware at the bottom with hardware virtualization support. Then we'll have the Linux kernel, also with some module for virtualization support. And then we're not running just apps, but we're running whole virtual machines. So multiple of them. And the virtual machine is really just a machine with the almost original picture inside each of the virtual machines. So inside the virtual machine, things still work the same. You have the syscalls. If that virtual machine is trying to do, trying to talk to the hardware, because it is thinking it is running on hardware, but it's not. It does an I/O, but it's an I/O because it's intercepted by the virtualization hardware and passed on through the kernel to this new thing, this application on the Linux platform. Sometimes, or oftentimes, it's QEMU. That's a hypervisor. So that's an application that drives the virtual machines, that makes them run. But it just emulates the hardware request in software. So QEMU is emulating a full physical machine. So if you boot a virtual machine, you will start with the BIOS, and then you do the bootloader and the whole thing. So that makes sense if you have to run existing Linux operating systems. But if you just want to run an app on the cloud in a virtualized environment, maybe we can do something simpler. And this is where the unikernel and the hypervisor, especially the smaller hypervisor, are combined. We've got the hardware still the same. We've got the Linux kernel still the same with the virtualization. But on top of that, we just run multiple unikernels. So now at least we can run multiple unikernels again. And the nice part is that those don't think they are running on a real machine, but they know they're running on a simplified hypervisor with a much simplified interface. So for me as a programmer, I don't have to, when I program these unikernels, I don't have to worry about all those really complicated physical machines that have backwards compatibility for 40 years, but I can just have a cleanly defined, cleanly designed, modern sort of interface to the hardware. So what I like about this new picture is that components have been cut away. Inside the unikernel thing is not a full kernel anymore, so that's millions of lines of code removed. And this simple hypervisor can also be much smaller. The one I've chosen to start with is about, I think, 5,000 lines of code. Well, QEMU, I've heard numbers of 1.5 million lines of code. So that's a lot of code that is needed to run an operating system to run your application. So it's starting to all feel a bit silly with all those big components. So the benefits of the approach I'm trying to take with the unikernel and the hypervisor is security. That's one of the interests I have. Much less code, no kernel, much smaller hypervisor, and the kernel that was in there before was written in C, so that's removed. I'll have to add some code to my Go unikernel, but it will be in Go. And Go is mostly memory safe. It's much harder to make mistakes that can be abused, so that's a win. You can also say that there is a performance gain with this approach. At least it's possible. I'm not so convinced myself. I think my programs usually run fast enough already, and it's also not that hard, not that easy to beat the performance of, say, a Linux machine that does things very efficiently. But it's true that you have to do less context switching with the unikernel because you are not. So the ring 3 to ring 0 boundary is not there anymore, and also you don't have to jump through the virtualization hoop all that often because you're not emulating a full machine anymore, but just a very simplified interface. So you'll have less context switching. One thing that is definitely faster is boot times, because you're not booting a BIOS and bootloader and all that stuff anymore. So the startup environment is much smaller. So there's one more benefit, and that applies only to me, and it's that I get to learn about the Go runtime and the toolchains and how it all works. So you need an excuse. This was a nice excuse to this project. So I picked an existing hypervisor that is small. It's called Solo 5. At the beginning of this year, I was at FOSDEM in a microkernels dev room where they had a talk about this project, and it felt like this was exactly what I needed because it was so simple and focused on security. It has a bunch of properties, a very simple boot mechanism. So instead of loading a full virtual machine disk image, it just loads an ELF image, an ELF binary like on Linux machines. It's very easy to create. It has only one single virtual CPU, fixed amount of memory at startup. You can configure it, but only at startup. There are no interrupts. It has a very simple hypercall mechanism that even I can understand. And it has very few calls for if you want to do anything special, like get the current wall time, print something to stand it out, read or write a network packet, and read or write a network or a disk sector. Pull, which is just sleep, which is interrupted when some event happens to the network, and there's halt. And really, this is the whole sort of interface that hypervisor provides. Finally, it uses TSC, this is timestamp counter for time, which is a Intel sort of instruction just to get time efficiently. So, with all that theory said, here is some workflow that I intend to be able to use at the end of this project. So I want to be able to go into any existing Go project, just download that code, compile it. So that's Go build, just as normal. I want to output it to this unikernel that I get. Normally it's a binary that you run on your Linux or Windows. Now it's a unikernel. And in order to compile the right support in, I will specify this hypervisor as my target operating system, this goose variable. And once I have that unikernel file, I want to be able to launch it, similar to how you would launch a virtual machine, by calling this hypervisor, pass it a network device, a block disk image, and this unikernel, and then we just boot and run my program. So the key thing here is that I don't want to have to modify my Go source code. So that means I would have to change a bunch of things to the Go toolchain, the Go compiler, and the Go runtime. So, the work that needs to be done. As I said, maybe first, are there questions so far about this unikernel hypervisor stuff? No?
So do you need to pass along the block device?
The question is, why do you need to pass along the block device? Well, you don't necessarily need to do it, but this is one of those things that systems provide, a network interface and a way to store things, because in the application itself you don't have access to a file system. But if you want to store something, you have to do it someplace, and that will be the block device. But you can run a network application that doesn't talk to a disk at all, and then you don't need that thing. So you can also launch an application without a net and a disk. But then it's probably not very interesting. But just a network could just work, yeah. All right. So the work to be done, as I said, I'm replacing something. I'm replacing that kernel with some.
Maybe maybe I'm missing something, but shouldn't there be something about memory, or you get the whole memory of the device?
I didn't.
It's just my lack of knowledge on this.
No, this is a good question. The idea with Solo 5, at least, with the hypervisor that I've chosen, is that you can, at startup, specify how much memory you get. And I didn't put it in the example in this line, because the default is 512 megabytes. I thought it was okay, but you can specify, I want to start it with 1 gigabyte, or maybe 2, or whatever. But yeah, you cannot change it. And that's in part because the goal of this hypervisor is to be really small and simple and not complicated. If you can go to other hypervisors that allow you to shrink and grow the memory. Good question. Thanks.
Actually,
another question.
For those system calls, are they for Intel or is it for specific to any CPU architecture?
Well, I'm targeting the 64-bit Intel
Actually,
architecture.
Why not just for Raspberry Pi? MD64.
Well, mostly because it's more work. I just want to have one thing.
Yeah.
I think the code I've written so far, at least, doesn't really do all that much Intel-specific things. But yeah, I'm just focusing on one target for now. But I think the same approach could apply to, say, an ARM device.
Yeah, it would be then too much fun because you can develop your own home theater system maybe, with just Go code.
Okay, I'm trying to find this slide. Here was. So I'm replacing that kernel I'm removing that kernel from the picture because I want to have this unikernel, but that means I'm removing a bunch of useful things that this kernel was providing. So it was providing files, I can open files, it was providing network, make TCP connections, and it was also having all these multiple applications as processes, and you could send signals to the different processes. That's all gone now. So as a unikernel, you have to sort of make a replacement for that. So the thing is that the hypervisor provides a raw disk and a raw network interface and one virtual CPU. So you have to make up those things that were removed by yourself. So you would have to add a file system, you would have to add a TCP IP stack, and you would have to see how much of those processes you need. So that's basically the work that needs to be done. And for that, I would have to modify the Go toolchain and the Go runtime. So so first, I already know now that the Go toolchain didn't need a lot of changes, so I'm not going to say too much about that, but the runtime does need quite a few changes. So I'm going to explain a little bit about the Go runtime, what it's doing, and what it is. So the Go runtime is just a normal Go package. Well, it's not entirely normal, but it's a Go package with consisting of mostly Go programs. It's in the Go source tree. Has a little bit of assembler, but it's mostly Go. And it's part of every Go binary that you create. If you compile a program, then that runtime gets linked into your program. And in fact, if you start up your program, if you run your program, the first instructions that get run are the runtime initializing its environment, setting things up, doing a bit of memory initialization, and so on. And then finally, at the end of the initialization, it jumps into your main function. But so before that main function happens, before your world as a Go program begins, a lot of stuff has already been done. Now, what is the Go runtime responsible for? Many of the core concepts of Go are handled by the runtime. So Go routines is clearly one of them. If you have a Go statement, like Go func, to make a new Go routine, that actually is translated by the compiler into a call into the runtime that just creates a new Go routine. And same thing for sending and receiving on channels. That always goes through the runtime. So the runtime is also responsible for scheduling your Go routines. If you try to send something on a channel, there's no space available, no listener, it will be blocking. So the runtime will schedule your Go routine away and run another Go routine. The runtime also does memory management. If you allocate some memory, that's done through the runtime, and the garbage collector is also started and driven by the runtime. And finally, the runtime does a bunch of smart stuff around efficient network handling. Now, the runtime does a bunch of things on its own, just with execution and memory moving, but it also uses system calls, of course, for much of its functionality. So those have been removed. Now, my approach is next. My approach to this whole problem, like I had to add some new stuff. How do you get started with a project like this? At first I thought, I have to make so many changes. How do I ever get something useful out of this? But I decided to start with an existing operating system, the support of an existing operating system, in my case OpenBSD, and just try to remove stuff, remove those the file support, and see if I could still have a working program, or a program that works otherwise fine but doesn't have access to files. And then I thought I would just remove sockets, see if that's possible. Maybe there's something I will find out along the way that makes this project completely impossible. But let's just take it one step at a time. And the third thing I was going to remove was processes. I ordered these in the order from simple to harder, at least as I was concerned. I thought the files would be easiest, so that I could get some quick feedback. Oh yeah, so my approach while working with this was to compile on my Linux machine or Mac OS machine, and then cross-compile to OpenBSD, and then copy the binary to an OpenBSD machine and run it. That way I still had a functioning toolchain, but I could still run those programs on OpenBSD. So first were the files. So the question I had was, do we really need files? I thought we really needed files because we use them a lot. With os.open, you open a file. But it turns out it's not used all that much, at least not in the standard library. So surprisingly few cases actually open a specific file. Turns out most of the opening of files is done in your applications, and then you will pass the file to maybe a standard library function, but that function will accept a IO reader or IO writer. So it has nice interfaces, meaning those files don't really occur all that much in the standard library. But there are a few cases, like the time zone database. If you don't have those files on the database, you will only have UTC. There's some network configuration, some usernames and group names, some TLS, Certificate Authority database, some MIME times, a few other files, but not too many. So I sort of quickly realized that this was not going to be a big problem, but I wanted to have somewhat working programs anyway. So I added support for fake files to the OS package. So I really removed all the system calls, like open and well, mostly open, and path-related system calls. So any attempt to open a file would fail. But I wanted to have some files available to the runtime. So I added this function add file, where you could just add a specific path with specific contents. And if you try to open that, you get a file handle to a fake file that a read would just return the data that you put in. So I would just have to, at initialization of a program, do a few of these calls, add some files, and then the rest of the program had access, especially runtime, had access to these configuration files. That made it work somewhat nicely. And I thought I can later on add a full file system. Don't have to do it now. I was not afraid that it could not be done. I was just afraid that it would take a lot of work. And I wanted to see if this next thing, the networking, would maybe be the stumbling block that would show this project is not possible. So I left the full file system support for later on, and I decided to move on to the network. So again, Go has networking abstracted away quite nicely in a net package. Has these dial and listen functions and a whole bunch of other things, but these are the basics. You get connections, so it's nicely abstracted away. But as I mentioned earlier already, we don't have a TCP/IP stack anymore. We only have a raw packet network interface. So yeah, we need to implement TCP/IP in Go. So again, that is there's a lot of work that I was not yet ready to do. But luckily, we can search on the internet for existing projects that do this, and I found one. I found one called NetStack, which is quite nice. It's by Google. It's a separate repository, but it's only a part of a much bigger project called gvisor, also by Google, which pretty much implements an operating system in pure Go, has different modes of operation, and it can run Linux applications, sort of. But it's a quite interesting project, but this NetStack thing is just the TCP/IP code of that project. And it works quite nicely. And it's even better because it has one package called GoNet, which is designed specifically to mimic the Go net package. So it also has a connection con, and it has sort of dial and listen functions. So if you use this package, you can already write your Go program, with this package, talk to a network interface on your machine, and run your own TCP/IP stack. So I was quite surprised. It saved me a lot of work. But it was not quite exactly what I needed, because my goal was to be able to run existing Go programs without modifications with this network stack. So I thought I'd try to integrate NetStack and use that as sort of the backend of the net package for making actual connections. So I made this separate branch in my Vmgo repository that does that. So it's net implemented with a NetStack backend. It only works on Linux AMD 64 because that's what NetStack implements out of the box. And it was so the amount of code needed to do this was surprisingly little. And it sort of works. You can go into your existing web application, for example. You can do go build. You have to specify these tags, NetStack. So these build tags is a sort of a mechanism to select certain files that you want to use from a package in your compilation. So with this, you will select the NetStack backend. If you don't put this in, you will still get the regular old networking backend, which also just still works. Then you get a program, and you're almost ready to run it, because you need to first specify the configuration of your network. I chose to specify that in an environment variable as pretty much as commands. So be verbose with your initialization, add a network interface with a certain MAC address, some MTU and network device, and print a trace of your packets. Then configure a specific IP address and add a default route so you can talk to the internet and also get traffic from the internet. And finally add a DNS server. And then if you run it, you can have just your Go program with a pure Go TCP IP stack. So that was a bit of a surprise that it was that easy. Now comes the hard part, processes. So if you've got a unikernel, you don't have processes anymore. You really just have only one sort of thread of execution. So really, processes and forking and exec is out of the question. So I just decided to remove support for that functionality. So this is clearly a big limitation of this approach. You cannot fork external programs. I removed it by just stubbing out those functions so they return errors. You can still call them, but they always fail. Now the much harder part is removing processes from the runtime. So the runtime depends in several places on having multiple processes to do its job. If you only have one virtual CPU, you don't have that concept anymore. So that's a bit tricky. Luckily, there is the WebAssembly port. It's experimental, it's in Go, but it sort of has a similar problem in that it also only has one thread of execution. So I figured I can probably copy some code from the WebAssembly port. But then, in order to get this further along, I did a lot of runtime reading and trying to understand what's going on in all the places. It's quite complicated, but I quickly realized that there's so much process-related code in the runtime, support code, like stuff that it needs from the operating system, that this was a good time to remove the old approach I had from compiling to OpenBSD and running binaries there to starting a new Goose variable, this thing that I showed in the workflow in the beginning. So I wanted to add this thing to the Go compiler toolchain to see, basically to really start running programs in this hypervisor. So also, again, this was surprisingly easy. You just need to find the right set of files to add some lines of code to, and then all the Go toolchain understands that this is now a valid new target. If you try to do this, your initial builds, your compiles will probably fail because you have lots of files missing in the runtime. So the thing to get it compiling is to add empty stub functions that don't do anything yet. But at least then you've got a compiling binary. So I was very happy to have my first Go program with this mechanism compiling. It's just an empty main function, doesn't do anything. But at least it was running and it was trying to execute instructions from the runtime that are always executed first. So that's actually why I added the first code. I didn't add code here in the main. I added code in the runtime and see what I could get. So it can do something. So this is the current state of affairs. I just can compile stuff. I can launch them with this hypervisor, which can create my programs. Now I do actually write something in that main function. I can create Go routines. They get scheduled and they get executed. So that's a thing. I can write from those Go routines to standard outputs. I can do some logging. So I can actually prove somewhat that it does something. I can already do some timekeeping. So you can get the current time. You can sleep a bit and just wait for a few seconds. And you can read in some form, you can read network packets, but it's not going properly through the right scheduling channels. So that's one of the next things I need to be doing, is proper networking I/O, then integrated NetStack thing. should not be too hard because it's already done once. Then support files in some way, maybe. And then the big thing, have more solid support. I have started understanding more of the runtime, but there's still a lot I don't know yet. And I'm sure there are many ways my current approach will go wrong. Then I'll have to see if more of the packages can be made to compile, which should not be too hard. And finally, there's a thing with preemption. That's a bit of a problem. As I said, you only have one virtual CPU, one thread of execution in your in this hypervisor, and there are no interrupts, so there's no way to preempt a running Go routine. So Go routine scheduling is also a nice topic, maybe for another talk, but suffice to say that with the current approach I'm having, there's a chance that one Go routine keeps running and not let any other Go routine run. So that needs a solution. Finally, the future. These are IDs, not necessarily plans, but IDs for the future, because it can be a lot of work. Maybe I need a different hypervisor target, so not Solidify, but something else, something that can do multiple virtual CPUs, because after all, Go is very good at executing multiple Go routines at the same time. I definitely need something for this preemption. There are interesting hypervisors on the market. One of them is Firecracker. It's an Amazon hypervisor. It's a fairly new one, designed to be simple and secure. And they use it to run their Lambda functions. There's Xen, which has existed for a long time, but they also have a more simplified mode of operation nowadays. There's Vertio, which is not a hypervisor, but only sort of a PCI-based device support. And there may be others that I don't know about, because I have not done a lot of virtualization stuff before this project. And finally, something else could be interesting, that is user interfaces. So I would need to have the hypervisor provide a display and mouse and keyboard, and then I can have graphical programs, but also in this very small environment. And finally, I need to definitely look at other projects. I did some searching before I started with this, because I thought, well, someone must have done this already. I couldn't find it. So I was working happily, and then Ilya told me last week that this basically already exists, and it's called Admin OS. That's at least one of the approaches, which is really very much the same idea, but then aimed at Xen. So, again, there may be other projects. If you know of any other attempts to do this, let me know. Final slide, really, at the end. This is just the GitHub repository where you can find the code. My email address if you want to contact me. I'm also on Slack, so you can message me directly. Finally, the Solo 5 hypervisor project is also on GitHub. You can also get that code. And with that, I thank you for your attention. Do we have any questions left? We've got one question. There's the...
Yeah. Could you please explain, Thompson, more about security benefits that you will get from this unikernel?
Yes, that's a good question. So the idea is, you could say that maybe you're not getting all that many security benefits. So normally, if you run an application, it also depends a bit on who you are in the big picture of running things in the cloud. So currently, you have, with virtualization at least, you'll have this application running in user space, and there's a security boundary towards the kernel, and basically I've removed that boundary. So if you're a cloud provider and you're running a virtual machine, and you are, as a cloud provider, in charge of the kernel, and you only run applications you only run applications of a user, and you have got them sandboxed away in user space. They have to first break into kernel space and then break out of the hypervisor. So I've removed, with unikernels, you remove one of those boundaries. So that's maybe you can say that this does not really improve security all that much. But on the other hand, many companies are now putting stuff in virtual machines because they are not so sure that they can trust the whole Linux kernels. There's probably going to, especially on a public cloud, it's a bit of a risk. The idea I'm having at least here is that you will have much less code running that can do weird stuff. So the smaller the amount of code, the better you can audit it, and the smaller you can keep it. There are some other, I think I have a slide here at the back. So I was a bit prepared for this question. Because you could say that you can also just do processes. So why would you, this is, now you're doing virtualization and all that stuff. You used to just run processes. So actually, Solo 5 has also a mode where it can just run as a process, but Solo 5 is a bigger project. One of the first points there says that still there's a whole Linux kernel running, and that's true because you've got this hardware, and then you've got the Linux host operating system, and then you've got these virtual machines on top of them. And I'm removing one of those kernels here, but there's still the big kernel, so you've got still all that code running. So maybe it's not all that secure, but I guess you can, in the future, maybe trim down that big Linux kernel, or you can say that you're running different parts of the Linux kernels in those different places. So to be really honest, I'm not entirely sure that from the application not running on a kernel, that will give you a lot of security benefits. Maybe it's more about being able to understand it. What is probably interesting, maybe more interesting, is the third line here, that in the future, that's something that the CPU manufacturers, especially AMD, is working on at the moment, is allowing you to run your virtual machines with encrypted memory. So the host operating system, the lower level thing, cannot read the memory of the virtual machine in plain text. So once you have that, once you have those kind of things possible, maybe that can provide some more security. But of course, still not really more security than your than the kernel running inside. But now then there is a big benefit because this kernel inside is really big and the interface to the hypervisor is really big. I'm saying a lot of stuff. I'm hoping I'm making some sense of this. Okay. Another question. Yes, we've got a question here. Can we throw the box? Nice one.
I was kind of waiting for the part of the processes because it's kind of interesting to re-implement the scheduler or the runtime with one thread on one virtual thread.
Yeah.
So do you have any more information to give us on that journey?
I think there is. So with the Solo 5 approach I'm taking, you only have one CPU, and that is the limitation. But it doesn't make it more. It doesn't really make it more complicated or change anything really. I think it's just that if you're targeting a Linux machine or BSD or Windows or whatnot, you need the operating system for a bunch of things, mostly for system calls. System calls can block. But now I've moved much of the stuff that used to be under the system call in the operating system. I've moved them to the Go runtime. So now, for example, the TCP/IP pure Go stack is really working with channels and things like that. So they are now handled by the Go runtime basically, and the Go runtime scheduling as Go routines. So that removes a lot of the stuff the kernel was doing, automatically moving it into the runtime, and it's doing that quite a fine job of that. So in that sense, we don't really need to do processes really in the Go runtime. There's just this preemption thing that is causing the troubles because that's at the moment that's not possible, and the Go runtime currently does need one separate process that once in a while checks if one Go routine isn't running too long and then interrupt it. So it will pretty much be forcibly asked to schedule itself away. So
exactly things like that, like from what I know, there need to be at least 2 kernel threads running for the Go runtime. I don't know if.
Yeah, you probably have more. There's for example, the network poller doing the network I/O, but again, the TCP/IP thing is in the Go space now. So you don't need as many with this approach. You don't need as many processes, but you do need some. You need at least one more mechanism than I currently have.
Thanks.
One more question.
So this goes back to your first question section. You're targeting Solo 5 in this picture. Yeah. Is that making things easier, or do you think it is nice? What would have happened if you had QEMU there in the picture?
Yeah, I think this makes it a lot easier because Solo 5 is the interface to Solo 5 is so simple. I can understand. I can just read it. In fact, I was at this talk at the beginning of the year. There was an explanation. I really thought I understood almost the whole picture at the end of one talk.
Because it's like those 7 or 8
exactly.
calls.
Yeah, but on the other hand, QEMU is emulating a full machine. It also has modes of emulating less, but what it's emulating is always a lot more. And if you want to make use of that, you will be reading a lot of specifications to really be able to talk to the hardware properly. So that's just a lot of work. And maybe someone else has done the work, but I would like to be able to understand what's going on.
It would look like an Intel processor. So you might be able to
No,
reuse more stuff.
There's two things here. So there's the instructions in your binary. You do a lot of instructions. Those get executed almost just the same, but sometimes you have these instructions that want to talk to the hardware. And on Intel, you've got these I/O instructions. So normal applications cannot run those, or at least they can try to run them. So it's more about the device emulation that you have to do with a normal machine. So you'd have to talk to PCI and to a network controller on the PCI bus. You have to do all that stuff just to be able to talk to finally some network interface to send some packet. All you want to do was send a big array of packets or bytes on a network, but you have to do all this network controller stuff.
So is it that in the, sorry, I'm going to wrap it up. In the Solo 5 case, you had a thing for saying send the packets.
Yes.
And in the QEMU case, you have to do I/O, where the end result is that some virtual device sends a packet.
Yes, yeah.
So it's a higher level abstraction.
No, yeah.
In the Solo 5 case.
Yeah, it's much more direct to what you want to do. So instead of having to program all the registers of a network controller, which you have to initialize first, and then you've got ring buffers and all that stuff, it's just many more steps and much more complicated. This is much easier. So I can understand it. So that's always what I like, if I can understand it.
Thanks.
Thanks. I'm fine with it.
Well, it's really an interesting subject. So from the implementation you have currently with network and files, even emulate, you could do some performance comparison, right? Because at the start there was this performance question mark.
Yeah.
So,
so I'm
have
pretty
you tried that?
No, I've not tried it. So first of all, the files thing is really just fake files, so those are not even real files. So that's not really a fair thing to compare. And second is the network stack. It is more in the state of it just works. It just starts working. So I have not been tempted to even try a benchmark. So I'm pretty sure that if you try to see how fast it is at the moment, it's not very fast. And that's also what I said. Like, we can do TCP/IP stack in Go. You can try to optimize it a bit maybe, but the Linux kernel's TCP/IP stack or any operating system kernel TCP/IP stack that's been used for a long time has been optimized to death. So if you want to beat it in your Go code, you're going to have a hard time. I mean, maybe there's some opportunities for optimization because you're not having to cross that security boundary, but yeah, so that's why I said I don't really believe, I'm not even doing it for the performance, but I also don't believe it's that easy to get better performance anytime soon. And so this is also a research project. I don't intend to make this a full, like the fastest production-worthy system yet.
No, okay, but just out of curiosity,
yeah,
it would be interesting to see if
I agree.
It's, how many magnitudes,
yeah.
orders of magnitude.
Thanks. Yeah? Oh, we've got more question. Oh, yeah, that's going to be a tricky one. Nice.
I loved your presentation.
Thanks.
About the runtime, I was slightly aware of it, that it even existed, but is it compiled every time from source? If you compile a regular Go app, or did you have to do some tweaking?
No, in theory, it's just compiled as a normal package, meaning it's not compiled every time. It's only compiled if any of the files change. So the Go build cache just takes care of the runtime just as any other program. So that was for development. This was surprisingly nice. Like I was thinking, I'm going to have to change the compiler, the linker to do something. Oh, let's reserve some weeks here. But they dive in and it's like, here's a few lines there. It's relatively. It's quite clean, but very clean.
Cool.
Yeah, happily surprised with that.
Thanks.
All right. I think that wraps it up.
No more questions?
Right.
Thank you, Michiel. Well, that brings us to the end of these talks. I hope you guys enjoyed it. And even better, I hope you guys get involved with us. So you can start by first joining us on Slack. You can scan the QR code and it should automatically invite you to join our Slack channel. We would also like to invite you, many of you, of the new faces, to become speakers, lightning talks, workshops, or even normal talks, even becoming hosts or sponsors. I would also like to note that Go Rotterdam has been opened, and they're preparing for their next meetup very soon. Yes. When was it exactly? So the 14th of November. So if anyone's interested, please join them. 28th. Oh, same day. Yeah. And also I would like to announce I just published the next meetup. It's gonna be in MessageBird on November 28th. So if anyone wants to join, please RSVP now. It hasn't been announced yet, so you guys have the first chance to join. It's also gonna be a bit special because it's the 10th year anniversary of Go, and I heard there's gonna be cake. Yeah. So I'd like to finish now, and also one more thing. All the talks, you can find them on the GitHub channel. So you can join and download the presentation or go over them over your own pace. So I would like to now invite you to a bit of socializing and drinking. Thank you.